Let us evaluate the integral of tan inverse of ax by x times 1 plus x square as x changes from 0 to infinity. We will be using the technique of differentiation under the sign of integral, or Feynman's technique. So we want to evaluate this integral. As you see that if we change the value of a, then the value of integral changes. So let's call integral to be equal to I. However, if we change the value of a, integral changes, so we call this I to be a function of a. Now we want to apply Feynman's technique, which is technique of differentiation under the sign of integral. So let us differentiate both sides with respect to a. I repeat, we differentiate both sides with respect to a. Differentiating both sides with respect to a. We got the integral IA to be equal to this. So we differentiate left side with respect to a, and we differentiate right hand side with respect to a. Now we observe that integral is just a long sum. Look at the symbol s. It can be written as something like this as well, or we can write it as long sum. Now further we know that derivative of sum equal to sum of derivative. Derivative of dda of sum equal to sum of dda, sum of derivative. So that we can say that derivative of integral equal to integral of derivative. Let's do that. Derivative of integral equal to integral of derivative. That's what Feynman's technique is all about. Once again, derivative of integral equal to integral of derivative. So, but you see that we got two variable a and x, so we will differentiate partially with respect to a. Once again, we will differentiate partially with respect to a. We just copy the original function tan inverse of ax. Once again, tan inverse of ax divided by x times 1 plus x square. We will partially differentiate with respect to a. Can we do it? When we say partial differentiation with respect to a, we will regard x to be a constant. So x and 1 plus x square, we don't have to differentiate it with respect to a. How about tan inverse? We know that derivative of tan inverse of a is 1 by 1 plus a square, but we got ax, so 1 by 1 plus ax whole thing square. But again we need to differentiate ax with respect to a, dda of ax. We know that dda of a is just 1 and x is just a constant, so dda of ax is just x. Of course, integral from 0 to infinity. Further we observe that we can cancel x out. Let's do it. And we get a simpler expression in the sense that we can simply integrate it by partial fraction method. Now, can we break it as sum or difference of two fractions? The answer is yes. Observe that 1 plus a square x square minus a square times 1 plus x square is simply equal to 1 minus a square, but we need to maintain the equality, so we divide by 1 minus a square, and we did maintain the equality. Okay, we can write this as difference of two fractions. In fact, this is equal to 1 by 1 plus x square minus a square by 1 plus x square will get cancelled, so 1 plus a square x square. Now integral of difference equal to difference of integral. So this integral can be written as 1 by 1 minus a square, 1 plus x square dx is x changes from 0 to infinity, minus integral of a square by 1 plus a square x square dx. Okay, now we can simply integrate it. You see that 1 by 1 plus x square, its integral is tan inverse of x. How about this one? See that dx can be written as d of ax, and so we should divide by a, and then d of ax. Once again, tan inverse of ax. Again, the limit is changing from 0 to infinity. Now tan inverse of infinity is pi by 2. Tan inverse of 0 is 0. minus a times tan inverse of infinity is pi by 2 and tan inverse of 0 is 0. We can take pi by 2 common and then we can cancel 1 minus a out and we'll be left out with just 1 plus a. What was the left hand side? Left hand side was di by dA. So derivative of I equal to this expression, I must be equal to integral of this expression but with respect to a. Pi by 2, that's just a constant, we don't have to worry about it. 1 by 1 plus a dA. So I equal to pi by 2 integral of 1 by 1 plus a is log of 1 plus a. Of course, plus some constant of integration. Can we determine this constant of integration? Observe that I is just a function of a as we have started with initially, and I a equal to integral 0 to infinity tan inverse of ax divided by x times 1 plus x squared dx. If we write a equal to 0, then we get tan inverse of 0 is simply 0 and integral of 0 is 0. So we see that I0 is exactly equal to 0. Observe that I0 is exactly equal to 0. So 0 equal to log of 1 is 0 plus constant, constant is 0. So IA is exactly equal to pi by 2 log of 1 plus a. Now let's write the explicit expression of IA. That's integral 0 to infinity tan inverse of ax by 1 plus x squared times x. So we can say integral 0 to infinity tan inverse of ax divided by x times 1 plus x squared dx equal to, once again, integral 0 to infinity tan inverse of ax divided by x plus 1 plus x squared dx equal to pi by 2 log of 1 plus a. Once again, this integral is simply equal to pi by 2 log of 1 plus a. And we are done.